Okay, section 7.5, algebraically defined vectors and the dot product. Algebraic interpretation of vectors. A position vector has an initial point on the origin. A position vector with terminal point AB is written as bracket AB, and A is the horizontal component, and B is the vertical component. The direction angle for a vector is the positive angle between the x-axis and the position vector. We usually label that as theta. Okay, so we are going angle theta over A up B. Okay, the magnitude and direction angle of a vector. The magnitude of a vector u, AB, is given by the absolute value of u, which is equal to a squared plus b squared. The direction angle, theta, satisfies the tangent of theta equals b over a. The vertical and horizontal components are given by a equals the magnitude of u times the cosine of theta. The cosine is the x component, okay, or the horizontal component. Okay, and b equals the sine. B is equal to the magnitude times sine theta, which is the horizontal component. The dot product of two vectors, u equals ab and v equals cd, is given by, this is how we kind of multiply vectors together, is a dot v, and it takes a vector and it makes it into a value, which is what we call a scalar. Okay, it's two vectors. When we dot them together, make a scalar, and we multiply the first components together, the x components together, multiply, and then we add that to the product of the y component. So the product of the x's plus the product of the y's give me the dot product. The geometric interpretation of the dot product is the cosine of theta is equal to the dot of u with v over the magnitude of u and the magnitude of v, product of those, where theta is between 0 and 180. Okay, vector operations. Okay, vector addition, we add the two x components together and we add the two y components together, a plus c and b plus d. Multiplying by a scalar times a vector is basically distribution. We multiply the scalar times the first component and the scalar times the second component. Subtraction is like adding a -1, basically. We distribute the -1, and when we add a plus negative c, which is a minus c, and b plus negative d, which is b minus d. Properties of the dot product. The dot product is commutative. The dot of u with v is the dot of v with u. The zero vector, which looks like this, 0, 0, that's the zero vector. Dotted with u is equal to 0, not a vector, a scalar 0. This is 0, this scalar. Just a value. Okay, let's see. B, we have kind of a distributive property here. U dotted with v plus w is u dotted with v plus u dotted with w. And u dotted with u is just the magnitude squared, which is really, if you think about it, what is the magnitude u? It's the square root. It's the square root of a plus b, or sorry, square root of a squared plus b squared. So this is really equal to a squared plus b squared. Okay, with no square root because the squared undoes itself. So we multiply a vector times itself, dot a vector times itself, we get the components, the sum of the components squared. Okay, and then k u dotted with v is the same as k times dotting u with v is the same as u dotted with kv. The k just gets basically multiplied through. And the k is a scalar. Okay, it's just a scalar value. Okay, find the magnitude and direction angle for u equaling 5, -4. Okay, so let's first start with the magnitude. The magnitude of u is equal to the square root of a squared plus b squared. Okay, that's going to be equal to the square root of -5 squared plus 4 squared, which is 25 plus 16, which is the square root of 41. So the magnitude of u is equal to radical 41. Okay. And I do my arrows a little bit differently. I only put one prong, I guess, to the arrow up, and that just means vector u. Okay. So as opposed to a ray, sometimes an arrow might mean a ray u, and so to make sure that there's no confusion on that, this has only one. The arrow only has one arm, basically. Okay, one prong. I don't know, however we want to say that. Okay, let's find the direction angle. The tangent of theta is equal to b over a. Okay, b is the second component, and a is the first component. So this is going to be equal to 4 over -5. So if I take the inverse tangent of -4/5, okay, so let's do that. Let's take the inverse tangent of -4/5. I get -38, so that doesn't help me much. Because, if I have a -38.7 degrees, where is that located? -38.7 degrees. Well, that's actually located in the fourth quadrant. But where is my vector pointing? Well, my vector is actually in the second quadrant. How do I know that? Well, it's -5, 4, right? -5, 4. Okay, so -5, 4. Okay, if we look at where -5, 4 is located from 0, 0 to -5, 4, that's going to be the second quadrant. Okay, so it's actually in the second quadrant. So I really need this angle here. Well, I have this reference angle of -38 degrees. -38.7 degrees. So how do I get it to the second quadrant? How do I use that reference angle to get to the second quadrant? Well, I just take 180 degrees minus the reference angle, 38.7. And when I add that together, what do I get? 180 minus 38.7. I could have just added 180 to my original, but this is going to be 141.3. So 141.3. So theta is 141.3 degrees. So it doesn't matter. It does matter which quadrant we're in, and we can find that by just looking at the components. Okay, find the horizontal and vertical components of a vector with magnitude 14.5 and a direction angle of 220. So A is equal to 14.5 times the cosine of 220. Remember, A is the horizontal component and B is the vertical component. Think cosine sine, right? So it's just the magnitude, we'll call that U. It's the magnitude, okay, of U is basically C here in my right triangle. Okay, and so we take U times the cosine of A, that gives me my horizontal component, and U times the sine of it's this is theta, it's A is equal to U times the cosine of theta will give me A, and U times the sine of theta will give me B, okay? Okay, so A is approximately what here? 14.5 times the cosine of 220 is negative 11.1, I'll say. Okay, so negative 11.1. B is equal to 14.5 times the sine of 220. Okay. Okay. And so B is approximately equal to 14.5 times the sine of 220 is negative 9.3. So this is negative 9.3. And so what's my vector? What would be my vector? My vector in component form would be 11.1 and negative 9.3, which is in the third quadrant. Okay, everything's negative, negative. Okay. And so once again, let me just look at these formulas. Like where are these formulas coming from? Okay, if I took the cosine of theta here, wouldn't that be A over the magnitude of u? Yeah, what would happen if I multiplied both sides by the magnitude of u? If I multiplied this side by the magnitude of u, and this side by the magnitude of that hypotenuse there, I would get A is equal to the magnitude of u times cosine theta. Oh, okay. And what about the sine of theta? Isn't that B opposite over hypotenuse? Isn't that B over the magnitude of u? Yeah, and what happens again if I multiply by the magnitude of u on both sides? Then I get B equals mu times sine theta. Okay, so that's where we get these formulas from. A is mu cosine theta, and a magnitude of mu cosine theta, and B is magnitude of u sine theta. And so I just thought I'd derive those for you because so it's not just coming out of thin air. Okay, let u equals 6, negative 3, and v equal 14, negative 14 and 8. U plus v, what's u plus v? Well, we're just going to add the x components together and add the y components together. So u plus v. Okay, so what's u? U is 6, negative 3, plus negative 14 and 8. Adding the u components together, or the x components together, the first components, that's going to be negative 8. Adding the y components together is 5. Okay. What about negative 1/2 times v? Well, v is negative 14/8. So this is, again, just like distributing. So negative 1/2 times negative 14, negative 1/2 times 8. This is going to be 7. This is going to be negative 4. Okay, what about 5u plus 2v? That's 5 times u, which is 6, negative 3, plus 2 times v, which is negative 14/8. Let's distribute the 5. That's 30, negative 15. Distribute the 2. That's negative 28 and 16. Adding the x components together, the first components, the a components, and if you like, 30 plus negative 28 and negative 15 plus 16, we end up with 2 and 1. Kind of nice. Okay, find the dot product of each. So dot product, we're going to multiply the first components together and then add that to the product of the second components. So the product of the x's, negative 5, negative 2, plus the product of the y's, 2, negative 4. This will give me one value. This is 10 minus 8, which is 2. Okay, B, this is going to be the product of the x's and the product of the y's. We're not adding here, we're multiplying. This is going to be 10 times 1 plus negative 1 times 10. That's 10 plus negative 10, which is 0. So the dot product is 0. Okay, so by the way, if the dot product is ever 0, that means that the vectors were orthogonal or perpendicular, or they were at a 90-degree angle. So if we did 10, negative 1 here, out 10, down 1, okay, we would get a vector like that. If we did 1, 10, 1 over 1 up 10, we would get this vector. And we see that this is a right angle. It is orthogonal. So the dot product of, if the dot product is ever 0, it is orthogonal or perpendicular. So this vector was 110, and this vector was 10, negative 1, and they did create, think of it like slope, so the reciprocal, the slope here would be 10 over 1, and the slope here would be negative 1 over 10, and they're reciprocal slopes. Okay. And if the slopes are reciprocal, then those lines would be perpendicular. Okay, find the angle between these. So we have the cosine of theta is equal to, let's go back to our formula here. The cosine of theta is equal to the dot product of the vectors divided by their magnitudes being multiplied. Okay, so we have u dotted with v over the magnitude, over the magnitude of u times, there's no dot here, it's times the magnitude of v. Okay, so I'm going to end up with a scalar over a scalar, just a number over a number, because u dot v, that's going to give me a scalar. The magnitude is a scalar, and the other magnitude is a scalar. So I would just end up with a scalar over a scalar, which is a scalar. The whole thing is a scalar. So let's break this down into its components. Let's look at the u dot v part of it. Okay, so u dot v, what's that going to be? That's going to be 5, negative 12 dotted with 4, 3. So that's going to be 20 plus negative 36, which is negative 16. Okay, so that's u dot v. Okay, what about the magnitude of u? Well, that's the square root of the a component of u, which is 5. Let me circle that maybe. That's 5 squared plus the b component of u, which is negative 12, negative 12 squared. So this is going to be 25 plus 144 square root, which is square root of 169, which everyone knows is 13. What about the magnitude of v? Magnitude of v, this is a 3, 4. So if I go 4 squared plus 3 squared, okay, a squared plus b squared, and then square root that, this is just a 3, 4, 5 right triangle. And so this is just going to be the square root of 25. I'll write it out. The square root of 16 plus 9, which is the square root of 25, which is 5. Okay, so now we need to put this all together. The cosine of theta is equal to negative 16 over 13 over 5. Negative 16 over 13 over 5. So this is negative 16 over, what's 13 times 5? What is that? Is it like 85? No, 65? I think that's 65. Let's make sure. 13 times 5. Yeah, 65. Okay. And so what I want to do is I want to go negative 16 divided by 65. But I want to take this value and I want to inverse cosine it. Second inverse cosine that value, and it gives me 104.25 degrees. Okay, so we would do theta is equal to the inverse cosine of negative 16 over 65. So theta is approximately 104.25, almost exact. Okay. Yeah. Oops. Like when that happens. Okay, there we go. Come on. There we go. Okay, find the angle between these guys. It's the same problem. Okay, cosine theta is equal to u dot v all over magnitude u, magnitude v. So let's do u dot v. What's the dot product there? That's going to be 24 and negative 24. Oh, interesting. So 24, I'll write it out. So this is 4, negative 3, dotted with 6, 8. Okay. So 4 times 6 is 24. Plus negative 3 times 8 is negative 24. That equals 0. So what did we say? When the dot product is 0, what do we get? We get a right angle. So this is a 90-degree angle. If you don't believe me, if I do the cosine of theta equals 0 over magnitude u, magnitude of v, well, what's the magnitude of u? We don't care, because 0 divided by anything is 0. So this thing equals 0. And what happens if I do the inverse cosine of 0? The inverse cosine of 0 is 90 degrees. So inverse cosine of 0 is 90 degrees. Okay, so those two vectors were orthogonal. Okay, so theta is equal to 90 degrees. Can we prove that they were orthogonal? Sure, we could just graph them. If we really wanted to graph this, okay, we would need 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now let's look at what's happening here with these. So 6, 8, we would need 1, 2, 3, 4, 5, 6, and then up 8. That's 6, 8 for v. That's vector v. Okay, vector u. Okay, vector u is 4, negative 3. So I'm going to go out 4. 1, 2, 3, 4. Okay, 1, 2, 3, 4. And then down 3. 1, 2, 3 is right here. And lo and behold, that is a right angle. Okay. You could multiply this vector by 1/2 as well, and you would see that this is 3, 4, which, or we could 3, 4 is on the way. Okay, 3, 4 is on the way to 6, 8. Okay, it's just halfway. And so the 4, negative 3 and the 3, 4, they do, in fact, create a 90-degree angle. If you even did the slope here, if you did b over a for each of these, the slope is negative 3/4 here, b over a, and the slope here is 4 over 3, because the 8 over 6 would reduce, and you would get opposite reciprocals as your slopes for these vectors. So they do create a 90-degree angle. Okay, two vectors are orthogonal if their dot product is 0, and orthogonal just means perpendicular. Okay, form of vectors. Okay, if vector v is equal to ab, then v is equal to ai plus bj, where I is equal to 1, 0, and j is equal to 0, 1. It's just, this is called standard basis form. You don't really need to know this until you go into calculus. Okay, and these are called your standard basis vectors. And we don't even talk about why it's called standard basis until differential equations. Okay, so coming attractions there. Okay, determine whether the following vectors are orthogonal. Okay, so let's just change these back to from standard basis form to component form. Call this component form. Okay, so to go back to component form, we just kind of drop the i's and j's, and we go radical 5 and -2. Okay, for that vector. This vector is -5, 2 radical 5. So are they orthogonal? Well, let's do the dot product. This is going to get me -5 radical 5. This is going to get me plus -4 radical 5 for a total of -9 radical 5, which is not 0. So it is not orthogonal. Okay. Okay, and I will see you guys in the next chapter. So good luck on your chapter 7 exam.